This talk is a conceptual design for a 20-ton space elevator climber, and I'm doing this for the KCL podcast. The space elevator has been my hobby / obsession since about 2004, when I started reading the book by Edwards and Wessling, Space Elevator, A Revolutionary Earth-to-Space Transportation System. Brad Edwards got a NIAC grant to design what has to be the cheapest way to build a space elevator, and it is still a must-read. They outlined all of the major issues for technical and business problems. So the basics of how a space elevator works. The space elevator is kind of like a string with a rock tied on the end. And pretend that I'm the Earth, and I have the string tied around my equator, which would be the middle of my belly, and I begin to spin. And as I spin, the rock points out perpendicular from my axis of spinning. That's the effect of the rotation of the Earth on the space elevator. And you notice there's a little ant walking out on the string. That would be the climber for the space elevator. So that ant can walk into space because my atmosphere only extends a very short distance from my belly. In more technical terms, what the tether does is it has a center of mass at geosynchronous orbit, and it extends from the surface of the Earth out to a counterweight at 100,000 kilometers away. And the interesting thing about this graph is that it shows you how gravity falls off as a function of distance. And what is significant about geosynchronous orbit is that, number one, you're orbiting around the Earth at the same speed that the Earth is rotating, so effectively you're fixed above a point on Earth. And the second thing is, at geosynchronous orbit, the gravitational effect of the Earth has dropped off to the point where it balances the centrifugal effect of the spinning. So that is the perfect place to put the center of mass, and the stress in the tether is maximum right at geosynchronous orbit, and it decreases towards the apex, and it decreases towards the Earth anchor. And you notice, because gravity is a 1 over r squared effect, it decreases very quickly. This is why it's so hard to get off the Earth. You have to exert a lot of effort near the surface of the Earth, but down when you're at a certain altitude, it takes much less power to drive the climber. And that actually complicates the design of the climber. So every design starts with requirements. And there are three very simple requirements here. We want to get to geosynchronous orbit in about a week. We want to carry as much payload as possible for a total climber mass of 20 tons. And in 2003, Edwards estimated 13 tons of payload and 7 tons of traction drive. And I'll show how that turned out. And 20 tons is considered the first commercial climber. Less than that, and we're talking about construction climbers, depending on what the tether is made out of. And then, of course, the third requirement is the climber must not fail in a way that jeopardizes the tether. So what are the assumptions for this design? The assumptions are that the tether is shaped like a ribbon with constant thickness. And because the tether needs to have the most efficient distribution of mass, it has what's called a tether ratio. So near the surface of the Earth, the ribbon is only 0.31 meters wide, and up at geosynchronous orbit, the ribbon is 1.55 meters wide, and the thickness of the tether is about 4 microns. 4 microns is very thin. It's much thinner than a sheet of paper. The design is a pinched wheel concept, which does not capstan. It doesn't wrap the tether around the wheels. I basically don't trust the capstan designs. I don't think you get a significant amount of friction from them. So the schematic or the block diagram of what a pinched wheel climber looks like is 2 wheels pressed by a compression mechanism against opposite sides of the ribbon, driven by motors. Each side is driven by a motor with brakes. And so there is a wheel compression mechanism, and there's an emergency eject mechanism. So that's the block diagram of the model. And the second assumption, which is the most important assumption in the design of the climber, is the coefficient of friction between the wheels and the tether. And this is a big item of study, but I had to assume that the coefficient of friction was 0.1. Carbon nanotubes or graphene are known to be slippery, and 0.1 is a good value. Below 0.1, and you're talking about solid lubricants, that means the tether would basically be too slippery and you'd have to squeeze on it too hard to make a feasible tether. If we can get the coefficient of friction higher than 0.1, design of the climber will be much easier. And the other thing I wanted to do with this design was to use commercially available parts if possible. Even though the components may not be the kind that you would select for a spacecraft, they're existence proofs of what should be possible. And these assumptions come from working on climber designs for the last 18 years and 39 years of being a mechanical engineer. So we start with the basics, okay? A design starts with a mathematical model. You've already seen the block diagram. So then we look at the mathematical model, and from the mathematical model, you begin to size the components. So this is the free body diagram of a wheel. You can see the wheel, and we only need to model one wheel because it's a symmetric system, and we treat the ribbon as a fixed boundary constraint in between the two wheels. So we can see the friction force, which is the force developed by the coefficient of friction between the tether and the wheel, the compression force that squeezes the wheel against the tether, the normal force, which is basically the reaction of the wheel on the opposite side of the tether, which produces the compression. We see the weight of the climber, radius of the wheel, and we see the torque required to drive the wheel, the coordinate system, and so on. So we write Newton's third law equations comparing the conditions of static climbing with some of the forces is equal to 0. Or if the climber is accelerating, we look at the acceleration terms. So then the next thing we did was we did a lot of research on the motors. This is still ongoing, and we need the highest power to weight ratio motors ever built. We need light, very powerful motors. And our survey of the market showed that motors designed for electric aircraft combine the need for lightness and power. And this is a graph of the power available in commercially available motors. These motors, since mass is on the y-axis, these motors are very heavy, and they're very typical industrial motors. Industrial motors are fixed motors, typically that the concern is not about mass, the concern is about rigidity. Down here, at the bottom of the graph, you get the motors that are designed for aircraft, the MRAX motors and the Magnix motors. And the next chart shows motor mass as a function of torque. It turns out that it's not power that drives the climber up the ribbon, it's the torque. And here, this chart actually shows you how the Magnix motors are in a class by themselves. They are the lightest motors for the most torque, and so we started the design based on a Magnix 650 motor, which delivered 2,814 Newton meters of continuous torque at 1900 RPMs and weighing 200 kilograms. That would be this point right here at the end. There's actually a smaller motor which I didn't use because the 20-ton climber needs the higher torque. And that's what that motor looks like when it's applied to an electric aircraft. And I included the drive electronics. So when you do the math, you say to yourself, okay, I have this much torque and I have this much friction available to me. How many wheels do I need compressed against the tether to be able to get enough torque to cause the climber to lift? So this was an early conceptual design that showed I needed 10 wheel pairs pressed against the tether, 20 motors, to give me enough torque to cause the 20-ton climber to lift. And this model, this CAD model, is missing many of the components that were developed later. So this is a much more developed model, and it also shows you what the climber looks like where the tether is much wider. So for example, if you look here, the tether is near Earth. This is the 0.31 meter wide tether, which is what sizes the width of the wheels. And this one shows you using the same width of wheel, but the tether is much wider. And you can see more systems have been developed in this picture because I basically just continued adding features. And then what ultimately happened was I added all of the necessary design features. Like, for example, here is the wheel compression mechanism. On the right side, the bearing and the axle and the wheel are in a fixed support structure that doesn't move with respect to the tether. But the left side is a motorized compression mechanism using a stack of Belleville springs that forces the wheel on the left side against the wheel on the right side and produces the compression. And what's not shown in this picture is in between these two halves of the climber, you need to have a tension member capable of resisting the compression that's being applied between the two wheels. So the next couple of slides show the quick disconnect mechanism, which allows you to separate the two halves of the climber at any altitude. It's also a motor-driven mechanism, which uses two gearboxes, actually three gearboxes, and it's a very simple pin clevis arrangement, and the turnbuckles can be extracted from their gearboxes. Basically, if you drive the gearbox too far, the turnbuckle falls out, which allows the two halves of the climber to separate and be jettisoned off the tether at any altitude. And that's another view of the mechanism where the two are being pulled together tightly, so everything is ready for compression of the wheels against each other. So where it got me is I developed a number of the subsystems for the climber to get to the point where I could measure the mass in the CAD model. I assigned materials to every component. I look at the mass in the CAD model, and unfortunately, when I got almost everything in there, with a few notable exceptions at the bottom of the slide, the traction drive weighed more than 20 tons. It could not even lift itself up, let alone any payload. Back to the drawing board. So my colleague Martin Lades and I talked about this for a long period of time, and he suggested looking at it in a different way, looking at it from the point of view of what do you have to do to a single wheel pair to force it to be able to lift some payload plus itself. So what I did was, I said, first of all, if the climber is already 20 tons, what happens if I just cut the number of wheel pairs in half? I go from 10 wheel pairs to 5 wheel pairs. That should make the mass of the climber half as much. Well, unfortunately, when you do that, you're also cutting out half the torque and half the capability of friction between the contact with the wheels. So that means the compression mechanism needs to be strengthened. You need to provide twice as much force squeezing the wheels together so that you get the same amount of friction to carry the 20-ton load. We still want to carry 20 tons. The quick disconnect mechanism needs to be strengthened to counter the additional force from the compression mechanism. And the Magnix motor doesn't have enough torque. That's the problem. The original design with 10 wheel pairs was based on the torque available from the Magni motor. If you're going to cut the number of motors in half, they have to deliver more than twice as much torque. The way to do that normally when you have a motor that isn't capable of delivering enough torque is to put gear reducers on it. Well, we did a lot of research on gear reducers and transmissions, which appears in the backup slides, and discovered that they are so heavy they actually weigh more than the motor. So putting a reducer on doesn't help. We need a motor the same mass as the Magni motor that delivers more than twice the torque of the Magni motor. This is where things get interesting. So basically, I said at this point, there is no commercially available motor that delivers the torque that we want at the weight we want. So let's imagine that there is a motor better than the Magnix motor that has enough torque, but it's not on the market today. And this is how we identified future motor development as absolutely crucial to climber design. What are the possible new technologies? Getting twice the torque out of a motor with the same mass as the Magni 650 is not trivial. Modern motors are driven at between 1 and 2 Teslas of magnetic fields, and super alloys saturate at over 2 Tesla magnetic fields. So one of the things you need to do is you need to jam more current into the rotor. Well, we're already at the limit of what copper wires can carry. So possibly graphene wires would be lighter than copper wires and have a greater current carrying capability. But high temperature superconducting motors might also avoid the mass penalty of the iron core, but it has a mass penalty associated with cryogenic systems. And I basically did not think it was reasonable to extrapolate beyond a factor of 2 in torque production for the foreseeable future. So the rest of the design, the 5 wheel pair design that I'm going to show you, is based on a 200 kilogram motor that delivers twice the output torque of the Magni 650. So after designing the extrapolated motor, I redesigned the climber for 5 wheel pairs. I used, instead of 10-ton jacks to apply the compression force against the wheels, I upped it to 20 tons. The quick disconnect mechanism could potentially be made from stronger materials without changing the size, so I didn't change the size of that yet. The shaft couplings between the motor and the axles need to be replaced. The problem there is the next size larger is huge, so that's a serious mass penalty problem. I replaced the aluminum structure with carbon fiber reinforced polymer, and the axles are now being bent by twice the force, so their deflection is twice as high. And I also looked at how to attach payload to a climber, because that's the point. The point of a climber is to carry payload, so we have to figure out how to connect the payload to the climber. And I was inspired by a talk that Elon Musk gave about how much fuel and liquid oxygen the Starship needs to go to Mars. So I designed liquid oxygen tanks supported by the climber, and that turned into a non-trivial design problem because the arms are also subject to 1 full gravity at the surface of the Earth. You'll notice a couple of things here. The arms are different lengths on one side of the climber versus the other because the side of the climber that has the compression mechanism on it, it already weighs more than the other side of the climber. Basically, the center of mass is offset from the position between the wheels. But for the climber to climb properly, you want the center of mass of the entire system to be on the tether. You don't want the climber causing the tether to rotate or to tilt as the climber climbs. So that means each of these 5-ton tanks of liquid oxygen has to be placed a different distance away. And what I discovered was the initial design had 4 of these carbon fiber reinforced arms, and that just wasn't enough material in bending to support a 5-ton load at that separation from the support structure of the climber. So that's the final version right there, which has a shear panel and 8 legs to hold up the LOX tank that's on the farther side of the climber. The last problem that I attempted to answer is how to dissipate the low-level waste heat from the climber. I haven't even dealt with the heat associated with power beaming to the climber, but I tried to come up with the area of a space radiator using radiation, thermal radiation into space in the neighborhood of the Earth. If you're away from the sun and significantly far away from the Earth, the temperature of space is about 3 Kelvin, so it's like an infinite heat sink. But when you're closer to Earth or when you're in sunlight, the temperature of space is actually significantly higher, and it takes quite a bit of efficiency away from a thermal radiator. Another problem with a space radiator is its size depends on the maximum temperature. This 83 square meter shell is based on a maximum temperature of 200 degrees C. Because many of the components of the motors, the lubricants for the oil, the insulation for the wires, can't be driven at higher than 200 degrees C. So one possibility to raise the temperature of the space radiator and keep the temperature of the oil that is recirculated around the bearings or the motor less than 200 degrees C is to put a refrigeration system in. Again, that's a mass penalty associated with a system that is not part of the budget at the moment. But this gave me an estimate for how much area I need to dissipate the low-level heat coming from the motors. And it becomes an assembly issue around the tether. The climber basically acts like two completely separate machines that are joined on opposite sides of the tether through the quick disconnect mechanism. And you can see that the payload is inside the heat shield. So this means that there is an order of assembly that has to be paid attention to in terms of mounting the wheels on the tether, in terms of mounting the payload on the climbers, and then mounting the heat shield around everything. So in conclusion, for years we've wanted a 20-ton climber to carry 65% payload ratio, 13 tons of payload, 7 tons of traction drive. And the best effort I was able to do, which is incomplete and missing a number of things, is a 5-wheel paraclimber to carry approximately 10 tons of payload, so it has a 50% payload ratio at any altitude. Now what makes this very, very significant is that the payload ratio for rockets is a function of how far away they're delivering the payload. The rocket equation is a terrible tyrant to rockets. And if you're talking about delivering payload from the surface of the Earth to the moon, you get less than a percent of payload ratio because you need so much fuel to get to the moon. So the difference between, you get a few percent of payload ratio for rockets to low Earth orbit, you get a smaller percentage to geosynchronous orbit, and a very small percentage to the moon. Whereas with the space elevator, you get a 50% payload ratio at any altitude. It's 50% at geosynchronous orbit, it's 50% if you let it go at some lower altitude and put it into a highly eccentric low Earth orbit, or it's 50% if you let it go somewhere in between geosynchronous orbit and the apex anchor so that it has enough speed to go somewhere else in the solar system. So the space elevator is effectively much more efficient at delivering large quantities of payload than rockets. And it's because it's not carrying its own fuel. It's getting power beamed to it along the tether. And that is basically what I have. I'm always welcome to entertain questions.